This is the second part of the semantic web vision and architecture lecture. So in the last class, we stopped by describing in brief the entire semantic web stack, which is also called the layer cake. Now we will be taking each component of this layer cake and try to provide example and illustrate further and see how they are connected with each other, right? So first we'll come to the component URI. Now if we show this to you and ask you what is this, in most of the cases the answer would be apple. Now I can argue that this is not really an apple, this is an image of an apple, right? So what is really happening? This image of the apple is basically replacing the real apple while we are trying to communicate the concept of apple. So here we are mentioning three things. One is we have the concept apple, we have the real world or real entity as apple, which is a real apple, and in your mental model the real apple has a representation as a concept, right? And this concept is related to other things like apple has a color, apple has a shape, apple has a weight, or apple is used to do something. So all these basically contributes to the definition of the conceptual structure of the real apple, right? But while we are communicating the idea of an apple, we use either a picture or a word or a sound, right? So this brings again to us the semiotic triangle, where you have a real world thing, the apple, which is basically the referent. You have the conceptual representation, which is your concept, and this concept refers to the referent, which is in our case the real apple. But while we are communicating, we have a representation of the apple, which is basically the string, the set of alphabets in a sequence, and this symbolizes the concept, right? But though they are different artifacts altogether, while you are communicating, these two, they really mix up with each other. So we really do not see the boundary between the symbol and the concept in a conscious way, right? So the point that I'm trying to make here, that this representation and this concept together, it is the substitute for the real world thing while we are communicating uh, the idea of apple from one place to the other place, right? So while we want to present this real thing on the semantic web, so we are basically substituting them with a representation and the conceptual structure, right? And this conceptual structure is basically the description of the real world thing. So this conceptual structure is basically the description of the real apple, right? And what does this description contains? It is basically a set of metadata, like what is the color, what is the shape, all those things, right? Now while we utter a term like apple, so this conceptual structure, it is evoked or triggered in our mind, and then we understand what we mean by the real apple. So this particular interplay between the representation concept and the referent is basically taken care of while the identification of an entity is perceived in the semantic way, right? And this is perceived through the uniform resource identifier, because we know that everything over the internet has a unique uniform resource identifier, and as we want our entities to be unique, they should be identifiable, and this URI has been taken to be the standard for representing the or identifying any entity on the semantic way. Now this URI is basically a schema which is used to identify any physical or abstract resource, and it is following this RFC 3986 protocol, right? Now these resources can be anything, any object or any abstract entity which has got a clear identity, like it can be a web page, it can be a book, it can be an abstract concept, or it can be a relation also. So this part will be coming back later, though at this point it will not be very much understood that why a relation should have a URI. So this part will become clear as we go forward. Now this concept of URI is already there on the internet. So the web domain, they are using something like URL, which is a specific form of URI. Or the books and the publications, they have ISBN or ISSN, or any digital object, they are identified by something called digital object identifier. So all these are instances of URI, right? Now this there is a very interesting relationship between this URI resource and metadata. So you can think of this resource to be the real world thing. Metadata is the conceptual structure, and there is a representation, and all these, they are connected via the URI. So let us see. So we have Taj Mahal, right? Now this Taj Mahal, it is a real world thing, right? Now while we are putting Taj Mahal over the internet, what we do, we create an HTML page or something similar to that and provide description of Taj Mahal in that page. So this description, again, it is called the metadata about the Taj Mahal, and this description can be unstructured like this text in textual form, or it can be structured like you have written this description in a, for example, XML form, right? Now this has got a representation. So this basically, this metadata describes the real Taj Mahal, right? Now this has got its internal representation. So in this case, you have an HTML based representation of the metadata, right? Now you have an identifier which basically connects all these together. So what we had, so this representation and this metadata put together, these two basically substitutes for this real world thing, right? And this www.tajmahal.gov.in basically identifies this composite structure, right? So while we are saying that we have an identifier for an entity, basically this identifier is pointing out to the composite structure of representation and the metadata description, right? Now this URI, they follow a syntax. This syntax can be thought of like you have a schema, and this schema can be like HTTP, FTP, something like that, or HTTPS. You have a host. So host can be a domain name like itkgp.ac.in, or it can be one Internet Protocol version 4 or Internet Protocol version 5, 6 address. It can have a port, so you can see this port is optional, right? And this 80 is a standard port for HTTP. You can have a path like say /database. So this /database is a path which is basically a path in your the file system of the server on which you have hosted the page. And along with that, you can have a set of parameters, right? So for example, you have a parameter like author, right? And the parameter has got a value, right? Which is example author. And finally, you can have a fragment. So which is basically, if you have a fragment, it is a part of the same document, right? So this is a generic syntax of URL. While you are publishing a data item on the internet or semantic web, you have to follow this scheme of presenting a URL. So the next part that we'll like to come is XML. So Unicode, as we have already talked about, it is a universal standard for representing any character set. It can be Bengali, it can be Hindi, it can be other languages, right? Now XML, perhaps we have many of us already know that what XML is, but for the sake of completeness, let us have a small discussion on it, right? Now, if you think about HTML, so HTML really looks at the presentational aspect of the uh, data, right? So how the data would be presented to the user. So for example, if you say H2, if you put this text under H2 tag, then it means that the style of this text, what is embedded between this H2, would be presented in a header 2 format, right? It would be made bit bolded, or the size of it would be a bit bigger than the normal text, right? So you have got different other tags which has got certain other meanings, but these meanings all they are related to the presentational aspect, right? Basically to do with the style of presentation, but it doesn't really take care of the structure of the data or the structure of the annotation, which XML takes care of. So XML takes care of the structure of the underlying structure of the data. So for example, a book has a title. Now irrespective of whether your title is being presented in H2 or other, it is a title, right? But here you see that we are not putting this H2. We are ignoring the presentational aspect, right? We are just interested in the structure of the data, right? So likewise, we have got author, we have got publisher, so on and so forth, right? So XML is a very good structure for exchanging data, because while we are talking about semantic web or the web of data, we are just interested in the structure of the data. The presentational aspect can be taken care of by HTML. So while we are exchanging data from one agent to the other agent, we want to know the semantics of the data, and the semantics of the data is embedded in the structure of the data, not in the presentational aspect of the data, right? So it is a good language or protocol, or not language, for exchanging data from one place to another place, right? So it allows, of course, the representation of the information in machine processable format, because it is structured. So that's why it is machine processable. And as we have discussed earlier, that the data and the structure of the data, and it is separated from the presentation of the data, right? And it is a meta language for markup. So what do we mean by that? So if you see HTML has got a fixed set of tags, right? So if you want to write a valid HTML document, you have to use all these set of tags. You cannot really use other tags. But in XML, the tags can be defined by the user, right? So it is a markup language. It is marking the parts of the data by tags, but you can define your own tag. So it is providing a language of the tags, right? So it is providing a language. Through this language, you can define your own tag, right? So that's why it is also called a meta language. And we have talked about this earlier, that it is a very good language to exchange data from one place to another place. Now coming to Rdf, which is, I guess, the most important component of this semantic web architecture. Basically, it provides the abstract representation of the data that are presented or that are stored in various schematic forms, right? So why do we need Rdf, right? So again, we were talking about the abstract representation of the data. So we were talking about abstract data representation. So the abstract data representation is needed because you want people to publish data, right? And you want people to consume data from the semantic web. Now, if you have very specific representation strategy, then it might work for one application, but it might not work for the other applications, right? So you want to facilitate data creation, data integration, and interoperation between one computing system to the other computing system, or one agent to other agent, right? So they need to have a common framework to talk to each other, right? And this particular facility is provided by the resource description framework, or in short RDF. And it is having a graph structure data model. We have seen in the earlier lectures that while we are talking about the bookstore examples, they have a graph kind of structure, right? So this RDF, they facilitate a graph based data model, right? And here every entity is identifiable, and this identifier is, as identifier, the URI is used, right? Now each data can be described in a very simple term by specifying three things. One is the subject, second is the predicate, and third one is the object. So we'll try to see as we go forward what are all these. So the resource description framework, the resource part is, it can be anything, right? So it can be anything under the sun. Only thing that you want to have is that every entity should be referenciable or identifiable by a URI. And it is a framework for description of the resources, right? Now this description, as we are talking about the apple, it has a color, it has a weight, it has got a shape, it is used to do something. So you can see that these are the properties or the attributes of the apple, right? So similarly, any entity you can think of, it can have different properties or different relationships that exist between different resources, right? And these relations, they can be represented as edges in the graph. So we'll see soon how these relations, they are represented as edges in a graph. So you are describing the resources, but it should be described in a standardized framework, right? Otherwise you see the whole network will fail, whole idea of semantic web will fail, because people or the agents or the computer program will not be able to talk to each other. So this framework is basically a combination of different web based protocol which are already existing. So this is the point I want to stress from the many a times, that the semantic web, they are not using new protocols. There are certain new protocols, but most of the protocols are borrowed from the internet, right? So URI, HTTP, XML, they are borrowed from the www or internet. And again, you want to provide the facility of reasoning, right? And only way you can have reasoning if you have a underlying formal model of the data, which is basically the semantics of the data. And the semantics of the data should be captured in a mathematical term. So that in that way we can assign formalism or mathematical explanation, mathematical background of the date on the data, if we can do that, we can write programs that can reason with this data, right? Now, this is an example of a graph or the abstract data model in resource description framework. So, you are describing a resource or entity called nick machine. So, you can see that we have written http://dbpedia.org/page/nick machine. So, this next nick machine is an entity described in dbpedia, right? Now, nick machine has a name, and here we are using, you can see that FOAF, we are using a vocabulary. So, you can write it in short FOAF colon name, right? And the name is nick machine, and this is represented in a rectangular box because this is a value. The name is a value, right? Nick machine is of type musical artists, right? Now this is represented in an elliptical node because this is another resource or entity, right? Many people can be an instance of musical artist, or the musical artists, they, I can say that they produce music. So the point is, you can describe a resource and entity, but you cannot describe a value. And as you cannot describe a value, you cannot have, so you do not have any outgoing edge. But for the resources or the entities, you can have outgoing edges like this, right? So similarly, the date of birth, the birth date is a value. So that's why it is represented in a rectangular box, right? And birthplace, it is an entity again, and we can describe this. We can say that this is part of, say, UK. So you can see that we have an outgoing edge from here. And this is what we are doing is called the alignment. So we are doing alignment here. We are just saying that this dbpedia.org/page nick machine is same as some entity described in freebase.com which has got an identifier like this, right? So these are same nick machine, here dbpedia, and perhaps this is also nick machine, and they are aligned with each other, right? So this is in the simplest form is a resource description framework, and you can see that how easy is this to conceptualize, how easy is this to represent and state, and finally to publish, right? So you just need to state three things about an entity. So what is the entity we are interested in? What is the attribute we are really talking about? So this is the entity that I'm describing, which is the subject. This is the property that I'm describing about the subject, which is P, predicate. And this is the value, which is basically also in technical term is called the object. And this object can be of two types. It can again be another entity or a resource, or it can be a simple literal value. So these values are also called literals. So you need to be conversant with the vocabulary of semantic web. So these are called literals or values, right? So the next thing is you have this abstract data model, right? Now you want to transfer this to, say, another agent. How do you do that? You have to translate this to a serializable form, and there are different serializable form. So one serialization form of RDF is called RDF XML. Now let us try to understand the structure that we have written here. So here we are just saying that which version of XML we are using. Now in this part we are defining something which is called the namespaces. right? So these are basically used to shorten a URI or one URL. So because these URLs would be used, or URIs would be used in later description. Now there is no point of writing this long string again and again, right? So if you do so, what will happen? Your data size will increase, right? So if you just, let's say you find out what are the instances of RDFs are there. So for example, you have here, so many places. Now you can write this RDF, or you can write this entire URI there, right? They are replaceable. Now if you don't have this, you just have this absolute URL here, right? So what will happen? The meaning wise your data will be same, but the size of your data will be increased, and as you are trying to reduce the size of your data, it's better to define them as namespaces, and these namespaces basically they are used to shorten the URIs, right? So for example, I am shortening this like www.w3.org/this and up to this to be named or symbolized as RDF. This friend of a friend URL is symbolized as FOAF, and this is the schema of which is followed in describing the entities in the DBpedia, and we know that schema is also called an ontology. So this is called DBAUL, right? So this is a symbol we want to use to replace this URI, right? Now let us see the description. So here we are describing the triples. So we have got subject, predicate, object. So these are together called a triple, right? So we are describing a triple here. So we are describing the resource nick machine, right? And what is the property we are describing? The property that we are describing is friend of a friend property. And what is the value? The value is nick machine, and the description ends here. So this is another description. What we are saying that the same entity like nick machine or DBpedia has a type like musical artist, right? So we are saying that nick machine is so by this what we are saying that nick machine, I'm just writing nm, is an instance of musical artist, right? And here again this is your subject, basically the nick machine. This is the property p, birthplace, and this is the value, which is Birmingham, right? Now coming to the next part, the sense making part. So the RDF is owl and rule. So this is called this is coming under the sense making part. So this is your sense making layer, and this was what? This was your web of data layer, right? So let us focus on this sense making layer part. So while we talk about sense, we need to concern about the semantics. So unless you have a semantics attached to an item or an entity or a data item, you will not be able to understand what does that data represent, right? Now the semantics emerge in two ways. One is through social communication, so which is called the emergent semantics. So you have human being in the society, they communicate with each other, and through communication they come up with the meaning of different things, right? And so for example, if you take computer, so back in say 1930s or 1940s or even 1950s, computer was not that understood by common people. Now at this point of time, I guess everybody understands what a computer is, though the sense of computer might be different to different people, right? So it is this kind of semantics, they emerge through social communication. But the semantics that we are focusing on is the explicit semantics, right? So we are explicitly stating that for a given entity, the semantics is understood by explicitly mentioning the metadata about the thing, metadata about the entity, right? And that is done very explicitly, and to to uh, to make it machine processable, machine interpretable, we need to assign a logic based framework. We need to use a logic based framework, which will be discussed in detail, onto it, so that the machines can understand the meaning of the data, right? And all this is achieved through three things. One is the Rdf schema, or the resource description framework schema, web ontology language or OWL, or rule interchange format RIF. Also we use semantic web rule language, which I have not written here. So the semantic web rule language, SWRL. Let us have an example of what we mean by Rdf schema, right? So let's say, so you have a data item to describe, like you have an album. The album, so this is of type album. So why we say that this particular entity, so this is an entity. So to the machine, this is an entity, right? Now, while I explicitly say that this entity has got RDF type to be album, then machine understands that this is a kind of album, right? Now, this has got a title, and we have used Dublin code as the language to say what do we mean by title, and the title is a literal, which is call of the value, right? Now this album has an artist, right? Now this artist I will see later. Now this artist has got a name, Pandit Hari Prasad Chaurasia, and has a type which is musician, right? Now, what do we mean by artist? Now, the artist, the album can have artist, right? So this is what I'm saying. Album has an artist. So the domain of the property artist. So artist is a property here. It's a relation between the album and Hari Prasad Chaurasia. So this artist is of type property. We are explicitly saying this, right? Now, this RTA property is already defined by a committee like W3C in RDF description and RDFS description, right? Now, we are saying that this RDF property is a subclass of resource. So, this is also described in RDFS, right? So, everything you can think of is a resource. So this is what semantic web assumes. So everything you can think of is a resource. A property is a resource, a class is a resource, everything is a resource, right? Now coming back to artist. So artists, the albums, they can have only artists, right? So the albums, they can have only artists. So that's why the domain of artist is album, right? So the value, so we are restricting the value of something that can have artist, right? So I'm saying that the albums can have artist, right? Or albums can have property artist. Now, if something has got a property artist, what value it can take? So it can take only values from the musician class, right? So if something is belonging, some entity is belonging to a musician, so that could act as the value of the artist property. So this is exactly what we can see here. Like this album, you can see that this is of type, this particular album is of type album, and it has got an artist. The artist is of type musician, Artist is Hariprasad Chaurasia, and Hariprasad Chaurasia is of type musician, right? Now also you are saying that this album, so this whatever we are starting with X, they are user defined, right? So this is defined by your individual organization, right? So this is this is a subclass of work. Again, work has been defined uh, mm, in your own database. So these are defined in your own data set. So these are all defined in your own data set. But even if you don't define this, this will be assumed like this is a subclass of RDFS resource because everything is a resource. Similarly, FOF person, it also belongs to or it also is a subclass of RDFS resource, even if you don't explicitly mention it, right? And this musician has been defined to be a subclass of person, and it is basically defined in your own database. And where do we define this semantics of artist, like the domain of artist and the range of artist? This is also has to be defined in your own database. So you can see this part is basically the data part, and this is basically the schema part. Now the schema can be a combination of user defined plus RDFS, right? So again, we will look into detail. We are just providing a glimpse of what we have in the entire architecture. Now, to describe OWL, I think it's best to come with an example and try to see what is happening here. So, RDFS, though very simple, it is limited in its expressivity, right? It cannot express many complex scenarios that we can see in the real world. So, for example, if we think this statement like SARS-CoV-2 is a virus that is not a DNA virus and contains spike protein. So this statement cannot be represented in RDFS because of many things. For example, RDFS doesn't support to say something is not something, right? So it cannot support that something is an intersection or end of two things, right? So it cannot do many things. So that's why this web ontology language has been standardized by W3C to make your knowledge base more expressive, right? Now let us try to see how we can represent this statement using web ontology language, right? So though we do not know the exact constructs that are there in web ontology language, but the names of the constructs, they are so much intuitive that you will get to know what we are really up to. So this is what we are describing. SARS-CoV-2 is a class, right? So this is a concept, right? So every concept is a class also. It can be represented as a class. So it is a subclass of something, right? So what it is a subclass of something? It is a subclass of a virus, right? That is what we can write. So, but it is a subclass of virus that has got some certain other mode description. So it is also not a DNA virus, and it also does not contains a spike protein. So it is an intersection of three things. It is a virus, intersection which is not a DNA virus, and intersection something that has or contain spike protein. Spike protein. So the SARS-CoV-2 is a subset of this set. So this is what we are trying to express using OWL, right? So this subset is taken care of by this RDFS subclass, and it is subclass of something that is a result of intersection of few things. So that's why I have written owl intersection of. So intersection of, now you can think this to be a list, and all these are intersected with each other. And list consists of V, not DNA virus, and has spike protein, right? So in this list we have a first. So we are just saying first RDF first. And what is the first? First is the virus. So we have written virus here. Now the list has, so this is your first. The list has a rest part of it. The rest part of the list is termed as rest. So we say RDF rest, right? Now what does this contain? It contains something like the second thing, again it is a list. It has got a first, so this is first. Now this first is something which is the complement of the set of DNA virus. So how do we write that? I write that as owl complement of DNA virus. So DNA virus is again a concept, again a class or a set. So it is a concept or a class, and it can be mathematically represented as a set. And as it is a set, we can take a complement of this set, right? Now the rest is only we are left with this has spike protein. Now as per our definition, it is something that can have a property which say contains. It can contain many things. It can contain spike protein and other proteins as well contains. But it should contain at least one spike protein. And this at least part is represented as there exists, right? So this is called there exists. So I am saying that there exists at least one relation for which the value is a spike protein. So that will give me the set of something that contains spike protein, right? So this is how we can write that in OWL, right? So we are saying that the rest of the list is HSP, and HSP can be described like it is a restriction over the property contents. And what is the restriction? The restriction is that it has a relation that has a value, that pick up a value that is spike protein, right? So this we will discuss again in greater detail, and things will be more clearer at that point of time. And finally, we are exhausted. We have already exhausted the list. We don't have any other to intersect. So mathematically, we can represent the SARS-CoV-2 concept or set to be a subset of intersection of virus, intersection of complement of DNA virus, and intersection of something that has got at least one relation which has got a value that belongs to the class spike protein, right? Now, in order to facilitate reasoning, we need to have rules, right? And rules, you know that they are like if A, then B, and exactly that will be captured in our rule interchange format. So it's again another language, right? So what we are saying here, if something, so this whenever we start something with a question mark, that means it's a variable. So this is a variable. So it has got a first name to be first. Again, it's a variable. And if we don't repeat something here, that means this x is repeating, right? So x has a surname last. So if this is so, x has a family name last, x has a given name first, and x name can be thought of to be a join of the first name and the last name separated by a blank, right? It's a very simple rule, right? Now one thing you can observe that we are following the same abstract data representation in which we have represented our data, same subject, predicate and object. So this x is the subject, this first name is the predicate, and this first is the object, right? You are using the same abstract data representation. And basically, if we go back to owl, these also can be represented as triple. Like you can say source cov2 is, so this is your subject and your predicate is rdfs subclass of, then the value is something else. This is an anonymous thing which is again described later. But the point that I'm trying to make out here, that we are following the same subject predicate object. So you can see that the generalization is, this is the kind of generalization that we are trying to achieve, that we can represent everything, whether it's a rule, whether it is a concept, everything that we can think of in semantic web, that can be represented using S, P and O. And this is basically the power of semantic web. Using these only three things are triple, we can represent anything under the semantic web. A bit more complex rule is like, if X has an ancestor Y and Y has an ancestor Z, then we can infer that X has an ancestor Z. So here this rule is representing something called transitivity. So we are saying X to, we are going from X to Y, X to Z, and from this we can infer that X is related to Z. Now, how to query the semantic web? So for that we need to have something called SparkQL, and this SparkQL, it is very interesting. It is an abbreviated form, right? But this is the acronym is a recursive acronym. So it is SparkQL protocol and RDF query language. We are using the same thing to define or expand the acronym, right? But the important thing here that I'll try to mention is that this language is, in the first place, is a query language. It's a query language as well as it is a protocol. So I'll come to the protocol part next, but let us talk about the query language part of it, right? So it is used to query a RDF data store, an RDF data store. Now this query has got different parts. So again, let us try to have a customary view of this thing. Again, the detail of it we'll be exploring later. So this prefix, you can see you can think them to be similar to the namespaces which we have defined earlier, right? So they are shortening the big URLs, right? So they are just symbols to represent longer URLs, right? So the first thing that we'll have, it will have a select clause, though you can have different kinds of queries. So this is a specific kind of query where you are retrieving certain data which can have different values, right? And what we are trying to get, we are trying to get something called author name, title and pages, but you can put anything like X, Y, Z. So these are variables. We are using this question mark to represent them as variables. So the form is, so this is what we are saying, that retrieve, and from is saying from where, right? So from which data set. So this from part is really optional. So if you are querying the data set from the same client, then you don't need to put this from part of it. And there are other scenarios where we'll be skipping this from part of it. And this where part of it, which is the main part of this query, here we are providing our intent, what exactly we want to have. So what we are trying to say, that there is something which is of type writer, and this something has got a name to be author name, and this something has got notable work to be worked, and this work has got number of pages to be some value, and this work has a title, some title, and we are limiting the result to 100. Maybe it can have say tens of thousands of results, but you are happy to see only 100 out of this. So this we can see shortly that this will also form a graph, and this graph will have nodes which might have variables like this, and these variables can be filled up by values, right? So that's why these are called templates or graph patterns, right? So let us try to visualize what we are trying to say in this graph pattern. So in the with the first statement, you can see in the first statement you have said author is of RDF type DBpedia owl writer. So you are saying author RDF type DBpedia owl writer. It has got a label to be author name. See, these are your variables, right? These are kind of blanks which you can fill by attaching real entities to it, right? Then this author has got notable work to be worked. This work has got a number of pages and it has got a label to be title. So you can see that it is becoming to be a graph, but in this graph you have got different variables. These variables can have different values. For example, this variable can be instantiated with Rabindranath Tagore. Now the Rabindranath Tagore can have multiple works like Bhanu Singher Padaboli, Valmiki Pratibha, Gitanjali. So for each of these, you can have these labels, right? You can have the number of pages. So for one author, you can have multiple values, right? So you are basically filling in the blanks to come up with the answers to this query, right? This SparkQL is also a query protocol. So why do we need this? So go back to the use case. So the agent, the Jane's agent, it is talking to the say independent rating agency to ask what are the ratings for a set of medical centers, right? Now it needs to formulate a query and transfer this query to the agent sitting before the independent rating agency. What this agent of the independent rating agency will do, it will run the query in its database, find the result and send the result back to the Jane's agents. Now you see that we are exchanging this agents, they are exchanging data either in a form of query or in a form of result. So to facilitate this transfer of the data, you need to have a protocol, right? So this SparkQL is again another protocol, right? So it is basically a method to transfer query or the responses from one end to the other end via HTTP. So we will be doing everything via HTTP protocol, right? So this SparkQL is basically URI. It will consist of three parts. One is the URI of the endpoint. So this is the endpoint where you can write queries for DBpedia data set, right? So you can visit this web URL and see what is there, right? So you can see a text box in which you can put your query and execute it in the first place. But as these agents, they cannot do a form filling. So what they can do, they can embed the query in the URL itself, right? So every data source, if they are publishing their data, they have to expose an endpoint. So these endpoints are called SparkQL endpoints, right? Now whenever someone is setting a query, the query has to has three parts. One is the URI of this endpoint. The second one is the the particular RDF graph that is to be queried. So it may so happen that the organization that might be having multiple graphs, right? So you say that I want to query graph 2. So you provide the URL of the endpoint, then followed by I want to query graph 2, right? But it can be optional. So if the endpoint, the dataset contains only one graph, then there is no point of sending which graph you want to query. And the third one is the query string. So basically the query string we have written, we have shown for the notable work and the author. So that is your query string, right? So these are the three components of one SPARQL query or SPARQL URI. So these will become a SPARQL URI, right? And it is simply a kind of HTTP colon slash something, right? Which you can hit and get a result, right? You can put that in a program and the program will receive the results, and you need to parse the result to find out the answers the agent has sent to your end. And all this can be done through RESTful API. So this is a kind of API architecture that is followed nowadays extensively. Finally, you have different entities in the system, in the semantic web. So it will be better that if you find alignments between this entity, and to strategy and a strategy to do that is called the unifying logic layer. So this is required, of course, because this data set, they are published in a distributed way, and the same data item can have number of different identifiers, right? So you have a same real world identity, real world entity, as they are used in different data sets or described in different data sets. The different data sets and as they are creating the data sets distributed in a distributed way, they can provide unique identifiers. For example, one can say Argentina .org, Argentina Football Club.org slash say Lionel Messi, and same Lionel Messi can be say BarcelonaFC.com slash Lionel Messi. So they are these two entities are same, but it is having two URL, right? So it is very wise to reuse the identifier. So you need to check whether is there any other data set which has used or described Lionel Messi. So in that case, you can use the URI. But again, you may not want to do that also. So if you want to reuse, you can use this URI directly. But if you do not want to choose that, so you want to have your own URI for Lionel Messi in your database, then you can use this owl same as, right? So you can use this to align two entities which you think to be same. Also you can use subclass of. So for example, you say L Messi is a subclass of is a type of footballer, and or club footballer, and it is a footballer. It is a subclass of footballer. Now, another description of Lionel Messi can again have something like club footballer, and it can say that it is a subclass of footballer. So in this way, you can connect them also. You can also use inference to detect sameness. So for example, let's say you have a book, and that book is described in different places, right? Now, the book they are describing, they are having the same, they should have the same URI, right? Now, they are, if it is like the book has been given multiple URIs in different places, but you know that, or ISBN in different places, but you know that a book can have only one URI or one ISBN, or a person can have only one passport number. So you can define some properties to be unique, like has passport or has ISBN. Now, if you see that some same book has got different ISBN or passport numbers, then you can merge them together by saying that a book cannot have two different passport numbers or two different ISBNs. In that case, you can say that the two books are same. And there are programs to do automatic ontology matching and alignment. Those programs can be used to do automatic alignments of the ontologies as well as the data that are described in different places. So I think I'm done with describing the semantic web uh, architecture stack, which is basically called the layer cake. And from the next class, we'll start talking about the detail of the individual components. But before going to that, we will discuss about something called knowledge representation in artificial intelligence. So there we'll touch upon a little bit what are the basic paradigms by which knowledge is represented in traditional AI, because those constructs will be used to define semantics of different constructs in RDFS or OWL and other things. So thank you for now. We'll talk about the things in the next lecture.